Something just happened in our solar system, and scientists across the United States are paying very close attention. A mysterious object from another star, older than Earth itself, has now reached one of the most critical points in its journey past our planet. Telescopes around the world have been locked onto it. Spacecraft have turned to watch it. And the biggest question everyone has been asking since the day it was discovered may have finally been answered. Is it just another comet or something far more unusual? Because what we've learned in the past few weeks about 3I-80LAS is not what experts expected. Its behavior changed. Its color shifted. It survived conditions that should have destroyed it. And for a moment, some scientists even wondered whether we were looking at technology, not nature. Tonight, we're diving into the newest discoveries, the biggest clues, and the truth behind the speculation. Because 3I-80LAS just answered the question everyone was asking, and the answer might surprise you. Before we begin, if you enjoy deep space mysteries and real science explained clearly, make sure you subscribe, like the video, and drop a comment. It really helps the channel grow. And I've got a quick comment task for you. Tell me which part of the United States you're watching from. East Coast, West Coast, Midwest, South, or your state. I read as many comments as I can, and I love seeing where everyone is tuning in from. The story of 3I-80LAS begins with a discovery that immediately sent ripples through the astronomical community. Because objects from outside our solar system are extraordinarily rare visitors, and every one we detect carries information about distant star systems that we would otherwise never be able to study directly. And when astronomers first spotted this object using the powerful survey network operated by ATUS, they knew almost instantly that it wasn't bound to the sun the way ordinary comets and asteroids are, because its trajectory was too fast, too steep, and mathematically impossible to explain if it had originated within our planetary neighborhood, meaning this object had traveled across interstellar space for millions, possibly billions, of years before arriving here, making it a messenger from another star. And that alone would have been enough to justify global attention. But what truly captured scientists' interest was how unusual it appeared even compared to the very small number of interstellar objects we've seen before. Because its brightness changed unexpectedly, its spectral signatures hinted at complex chemistry, and its behavior near the sun didn't follow the patterns astronomers normally rely on to predict how comets evolve, which is why the moment it approached its closest point to Earth became so critical, since proximity means better data, sharper images, and more accurate measurements of composition, rotation, and structure. And as that moment approached, observatories across the world coordinated observations, including ground-based telescopes, orbital instruments, and even spacecraft positioned millions of miles away, some of which belonged to NASA, all aiming to capture as much information as possible before the object continued its escape back into interstellar space forever. And what made this observational campaign especially important was that 3I-80LAS had recently passed behind the sun from Earth's perspective, temporarily disappearing into the glare, which meant scientists had to wait anxiously to see what condition it would be in when it re-emerged, because solar heating can dramatically alter comets by causing volatile materials like water ice, carbon dioxide, and carbon monoxide to sublimate, transitioning directly from solid to gas, which in turn drives jets of material into space, changes the object's brightness, and sometimes even breaks the nucleus apart entirely. And the question was whether 3I-80LAS would survive that intense solar encounter intact. Since interstellar objects may have very different internal structures compared to native solar system comets, perhaps making them more fragile or, alternatively, more resilient. And when it finally emerged from behind the sun, astronomers immediately noticed something surprising. It was still there, still active, and in some ways even more interesting than before, because its brightness curve suggested ongoing outgassing. Yet the composition signatures indicated unusual ratios of certain elements, including metals that aren't typically dominant in comet atmospheres, which prompted deeper analysis into how cosmic rays, high-energy particles traveling through the galaxy, might have chemically altered its surface during its long journey between stars, effectively baking its outer layers over millions of years and creating a crust that behaves differently when exposed to solar heating And this idea is important because it highlights one of the key educational insights from studying interstellar visitors, namely that space between stars is not empty but filled with radiation fields capable of modifying matter over geological timescales, meaning objects like 3i Gatios can act as natural laboratories for understanding chemical evolution across the galaxy, offering clues about how organic molecules form and survive in environments far from any planetary system. And as new data came in, astronomers also began tracking subtle changes in the object's color, which shifted toward different wavelengths over time, suggesting variations in dust particle size or composition being released from the surface. And this phenomenon matters because color measurements allow scientists to infer physical properties without directly sampling the material. For example, redder hues often indicate organic, rich compounds known as tholins that form when ultraviolet radiation interacts with simple molecules, whereas bluer scattering can indicate smaller or fresher dust grains. And by modeling these changes, researchers can reconstruct how the object's surface layers are structured, essentially performing remote geology on something millions of kilometers away. And another major milestone came when spacecraft observations provided a perspective impossible from Earth alone, including images captured from orbit around Mars, which offered different viewing geometry and lighting conditions that helped confirm the presence of jets emanating from the nucleus, reinforcing the idea that the object is actively releasing gas and dust rather than being an inert rock. And jets themselves are fascinating because they arise from localized regions, where sunlight penetrates the surface and heats volatile pockets beneath, creating pressure that vents material outward like natural thrusters, which can even alter the object's trajectory slightly through what's known as non-gravitational acceleration. And measuring that effect allows scientists to estimate how much mass is being lost over time, providing insight into internal composition and structural integrity. And this leads directly into one of the biggest questions everyone was asking: could 3i Gatios be something artificial, perhaps even a piece of alien technology? A speculation that gained traction not because of strong evidence but because unusual phenomena tend to capture public imagination, especially after earlier debates surrounding previous interstellar objects. And from an educational standpoint, it's important to understand how scientists evaluate such claims, since extraordinary hypotheses require extraordinary evidence, meaning researchers look for signs like unnatural acceleration patterns inconsistent with outgassing, radio emissions indicative of communication signals, geometric shapes inconsistent with natural formation, or spectral signatures suggesting manufactured materials. And in the case of 3i Gatios, multiple radio observatories conducted targeted searches for technological signals and found none, while the observed motion could be explained by natural cometary processes, demonstrating the scientific method in action. Hypotheses proposed, tested, and either supported or rejected based on data rather than speculation, and yet the investigation itself remains valuable because it pushes instrumentation and analysis techniques forward, ensuring that if a truly anomalous object ever did appear, we would be better prepared to recognize it. And beyond the question of artificial origin, another topic drawing attention was whether the object would survive its solar encounter long enough for continued study, since thermal stress can fracture materials, especially if they contain volatile pockets that expand unevenly, and models predicted significant mass loss, but not necessarily complete destruction, which appears consistent with observations so far, though astronomers continue monitoring for fragmentation events. Because if the nucleus were to break apart, it would offer a rare opportunity to study internal layers directly, revealing pristine material shielded from cosmic radiation for billions of years. And that possibility excites planetary scientists because understanding the internal composition of interstellar bodies helps answer broader questions about planet formation in other star systems, such as whether water-rich planetesimals are common throughout the galaxy, which has implications for the prevalence of habitable worlds. And stepping back, the entire story of 3i Gatios also illustrates how modern astronomy operates as a global collaborative effort, combining data from different wavelengths, visible light, infrared, radio, and different vantage points to build a comprehensive picture, something impossible just a few decades ago. And it highlights how survey systems continuously scan the sky for transient events, detecting not only potentially hazardous asteroids but also rare phenomena like interstellar visitors. effectively turning Earth into a cosmic observation platform connected to a network of instruments spanning millions of kilometers. And perhaps the most profound aspect of this moment is philosophical rather than technical, because every interstellar object reminds us that our solar system is not isolated, but embedded within a dynamic galaxy where material is constantly exchanged between stars through gravitational interactions, stellar evolution, and planetary formation processes, meaning the atoms in objects like 3i ATLAS may have originated around entirely different suns long before our own formed, making its arrival here a convergence of cosmic history on an unimaginable scale. And as scientists continue analyzing the latest data gathered during its closest approach, they are gradually piecing together answers to the questions that sparked worldwide curiosity, including its composition, structure, origin, and behavior near the Sun. And while some mysteries remain, the emerging picture is already reshaping our understanding of how interstellar bodies evolve, how radiation alters matter over time, and how common such visitors might be, which ultimately leads to the realization that this is likely not the last interstellar object humanity will study, but it may be one of the most informative, because each new detection builds on the lessons of the previous ones, improving detection algorithms, refining theoretical models, and inspiring future missions that could one day intercept such an object directly, turning distant observation into hands-on exploration. And that possibility, the idea that a fragment from another star could someday be sampled in a laboratory on Earth, transforms what might seem like an abstract astronomical event into a tangible step toward understanding our place in the universe. Which is why the moment 3i ATLAS reached this critical point in its journey wasn't just another data collection window, but a turning point in a scientific investigation that has captured both expert attention and public imagination, setting the stage for the revelations that would follow as researchers finally began answering the question everyone had been asking. As 3i ATLAS continued its journey through the inner solar system, the scale and sophistication of the observation campaign reached a level rarely seen for a small celestial object, because unlike ordinary comets that return periodically and can be studied across multiple orbits, an interstellar visitor offers only one fleeting opportunity before it disappears forever into deep space, which meant astronomers had to gather as much information as possible in a narrow window of time. And this urgency drove coordinated efforts involving space-based telescopes, planetary probes, and some of the most advanced ground observatories on Earth, including instruments operated or supported by NASA and European Space Agency, each contributing unique capabilities across different wavelengths of light. And understanding why multi-wavelength observation matters requires a brief dive into astrophysics, because visible light alone only reveals reflected sunlight from dust particles, whereas infrared wavelengths allow scientists to measure heat emission and determine temperature. Radio observations can detect molecular signatures and search for artificial transmissions, and ultraviolet measurements can reveal ionized gases interacting with solar radiation. So by combining these datasets, researchers can reconstruct not just how the object looks, but what it is made of and how it behaves physically under solar heating. And one of the most intriguing developments during this period was the confirmation that 3i ATLAS had changed color again, a phenomenon that may sound cosmetic, but is actually deeply informative, since color variations indicate shifts in particle size distribution and chemical composition within the coma, the cloud of gas and dust surrounding the nucleus, which in turn reflect processes occurring beneath the surface, such as the exposure of new material after crust layers fracture or the depletion of certain volatiles as they are exhausted by repeated heating cycles. And scientists noticed that the spectral slope of reflected light had evolved toward wavelengths, suggesting finer dust grains were being released, potentially indicating that the object's surface had begun breaking down more aggressively as it approached perihelion, the point closest to the Sun. And perihelion passages are critical in comet science because they represent maximum thermal stress, with solar radiation increasing dramatically according to the inverse square law, meaning that if distance to the Sun is halved, the energy received increases by a factor of 4, which can trigger explosive outgassing events known as outbursts, sometimes increasing brightness by orders of magnitude in a matter of hours. And indeed, observations showed episodes of rapid brightening that initially puzzled astronomers because they appeared too intense for the estimated size of the nucleus. prompting speculation about either unusually volatile, rich composition or structural fragmentation exposing fresh material. And follow-up analysis suggested that both factors might be involved, since interstellar objects may contain volatile compounds preserved under extremely cold conditions for eons before encountering a star again, effectively storing chemical energy that is suddenly released when heated. And this ties into a broader scientific question regarding how planetary building blocks differ across star systems. Because if three-eyed LS contains higher fractions of certain ices compared to solar system comets, it could imply that its parent system formed under different temperature or chemical conditions, providing indirect insight into planetary formation environments elsewhere in the galaxy. And another remarkable milestone came when spacecraft orbiting Mars captured images of the object from millions of kilometers away, offering parallax measurements that improved orbital calculations and confirmed subtle accelerations caused by outgassing jets. And this multi-planet observation approach demonstrates a key concept in astronomy known as baseline separation, where observing an object from widely separated points in space allows more precise triangulation of its position and motion, much like how human depth perception relies on two eyes spaced apart, except on an astronomical scale that, yes, can be entire planets, and the data obtained from these observations helped refine estimates of the nucleus size, rotation period, and mass loss rate, which are essential parameters for modeling the object's evolution and predicting whether it might survive future solar encounters before leaving the solar system entirely. And one particularly fascinating discovery involved the detection of a sunward jet, material streaming toward the sun rather than directly away, which initially sounds counterintuitive, but actually arises from complex interactions between gas pressure, rotation, and solar radiation forces, because jets emerging from rotating surfaces can be redirected by momentum and radiation pressure, creating curved trajectories that appear to point in unexpected directions. And analyzing jet geometry allows scientists to infer rotation axis orientation and surface activity distribution, effectively mapping the object without ever seeing its surface directly. And this level of remote inference highlights the ingenuity of modern astrophysical techniques, where indirect evidence is transformed into detailed physical understanding through modeling and simulations themselves played a major role in interpreting 3i-80LS data, particularly dynamical simulations tracing its path backward through the galaxy to estimate its origin region, which involves integrating its trajectory under gravitational influences of stars and galactic tides over millions of years, a process complicated by uncertainties in stellar positions and velocities, but still capable of identifying probable birth environments such as dense stellar clusters where gravitational interactions can eject planetesimals into interstellar space. And if 3i-80LS did originate in such a cluster, it would support theories suggesting that interstellar objects may be far more common than previously thought, potentially numbering in the trillions throughout the Milky Way, with countless passing through our solar system undetected due to their faintness, meaning improved detection systems could dramatically increase discovery rates in coming decades. And while the scientific community focused on composition and dynamics, the public conversation remained heavily influenced by the lingering question of whether anything about the object suggested artificial origin, a question amplified by social media and sensational headlines. But systematic radio searches conducted by observatories found no evidence of technological signals, reinforcing the natural explanation and illustrating how science distinguishes between possibility and probability, because while it is logically possible for an interstellar object to be artificial, the overwhelming prior probability based on known physics favors natural formation unless compelling evidence indicates otherwise. And this reasoning framework, Bayesian inference, is central to scientific thinking, combining prior knowledge with new data to update confidence in hypotheses, and applying it to 3i-80LS strongly supports the conclusion that it is a natural comet or comet-like body shaped by cosmic processes rather than engineering. Yet even dismissing the alien spacecraft idea does not diminish the object's importance, since its unusual chemistry, structural resilience, and dynamic behavior still challenge existing comet models and may lead to revisions in our understanding of how icy bodies form and evolve. And perhaps the most dramatic development during this chapter of its journey was the realization that despite intense solar heating, the object had not disintegrated as some models predicted, leading some researchers to describe it informally as being cooked, meaning its outer layers had undergone significant thermal processing, but still structurally intact, which suggests a stronger or more cohesive internal structure than expected, possibly due to compaction under cosmic radiation or the presence of refractory materials like silicates mixed with ices, and this resilience provides clues about mechanical properties of interstellar bodies, information crucial for any future mission attempting interception or sampling, because mission planners must know whether such objects are fragile rubble piles or cohesive masses to design appropriate interaction strategies. And looking ahead, scientists also began modeling what would happen next as 3I Vatios recedes from the Sun, predicting how its activity would decline, how its rotation might change due to asymmetric outgassing torques, and whether additional fragmentation events could occur, all of which feed into long-term monitoring plans to continue observations as long as it remains detectable, and while eventually it will fade beyond telescope reach. The data collected during this intense observation period will occupy researchers for years, leading to scientific papers, improved models, and perhaps new theoretical frameworks for interstellar object evolution. And from an educational perspective, the story illustrates how astronomy is not just about discovery moments but sustained analysis, collaboration, and iterative refinement of understanding, where each dataset is cross-checked, uncertainties are quantified, and conclusions are revised as new evidence emerges, embodying the self-correcting nature of science itself. And as this chapter of the investigation unfolded, one thing became increasingly clear. The question everyone had been asking, what exactly is 3I Vatios, was finally moving from speculation toward evidence-based answers, setting the stage for deeper insights into its origin, composition, and ultimate fate as it continues its brief visit through our cosmic neighborhood before returning to the vast darkness between the stars. By the time the latest wave of observations had been analyzed, the scientific picture of 3I Vatios had become far clearer than at any point since its discovery, and the conclusion emerging from multiple independent research teams was both reassuring and profound, because the object that had sparked speculation, debate, and even whispers of alien technology turned out to be something arguably more fascinating. A natural interstellar comet unlike any humanity had studied before, shaped by processes that occurred around another star long before our Sun existed, and confirmed through coordinated measurements involving telescopes on Earth, spacecraft instruments, and radio observatories supported by organizations like NASA, which collectively found no evidence of artificial signals, engineered materials, or motion inconsistent with known physics, instead revealing clear signatures of volatile outgassing, dust production, and chemical composition consistent with a primitive icy body, albeit one altered by millions of years of exposure to galactic cosmic rays. And this answer matters not because it dismisses the extraordinary, but because it replaces speculation with knowledge, showing that the universe is capable of producing objects with behaviors that initially appear mysterious yet ultimately deepen our understanding of natural processes. And perhaps the most important realization is that 3I Vatios represents a sample of planetary building material from another solar system, meaning scientists are effectively studying extrasolar geology without ever leaving home, providing clues about how common water, organic molecules, and rocky components might be throughout the galaxy, which connects directly to larger questions about planet formation and the potential for life elsewhere. And as the object now continues its outbound journey, gradually fading from view as it accelerates back into interstellar space, it leaves behind a legacy of data that will influence research for years, along with a powerful reminder that our solar system is not isolated but part of a vast cosmic ecosystem where material travels between stars, and that realization, more than any speculation, may be the most extraordinary answer of all.